Welcome to today's Explainer. We're diving straight into Sir Abrar Ali's notes to explore a genuinely fascinating connection. You know that basic circuit theory from high school physics? Well, it turns out that is the absolute secret to keeping massive, real-world power grids running smoothly. Let's get right into it.
Okay, let's dive into this. It is so tempting to just jump straight into the heavy engineering manuals when learning about modern power grids, right? But why do these advanced systems still rely so heavily on basic circuit theory? Well, the truth is, before we can even begin to grasp the complexities of advanced grid tech, we'd literally have to revisit the fundamentals. Without understanding exactly how a simple series or parallel circuit behaves under pressure, all the advanced stuff, it'll just look like magic. Or, honestly, worse, a recipe for absolute disaster.
So, to answer that opening question, here is our roadmap for today's analysis. First, we'll explore the world of facts, then break down the two types of compensation. After that, we'll see how a StatCom works, compare series versus parallel resonance, and finally wrap up with the real-world engineering stakes.
All right, let's kick things off with Section 1, the world of facts.
If you think about how power transmission used to be managed, it was actually pretty rigid. You basically just had simple mechanical switches throwing giant capacitors onto the grid. But looking at Sir Abrar Ali's notes, it is fascinating to see how the industry has completely shifted. We've moved far away from that clunky mechanical switching to a highly flexible, dynamic system. It's a real game changer. But here's the catch. To actually understand this new flexibility, we need a rock-solid grasp of the underlying circuits. It is not just an on and off switch anymore. It's a living, breathing electrical ecosystem.
That brings us right to Section 2, two types of compensation.
So how do we physically balance and support these huge transmission lines? Grounding this whole abstract concept of grid compensation usually boils down to just two things: adding capacitors in series or adding them in shunt, which is really just a fancy way of saying in parallel. Sure, reactors get used sometimes, but it's mostly capacitors doing the heavy lifting here. When we talk about flexible transmission, we are fundamentally talking about exactly how we manage these series and parallel additions to keep the whole system perfectly stable.
Now, what's really interesting about this next technological marvel is the shift in approach. Let's look at Section 3, how StatCom works.
This part of the material honestly blew my mind a little bit. A StatCom, or static synchronous compensator, completely flips the script. Instead of relying on massive, bulky physical capacitors just sitting out in a substation, a StatCom manages the grid purely through manipulating a DC source. It's essentially using smart electronics to digitally recreate the effects of those giant physical parts. It generates the active currents that do the actual work and the reactive currents that sustain the voltage. This right here perfectly highlights why modern grid tech is so incredible. It's gotten way smarter, not just bigger.
Which brings us to Section 4, series versus parallel resonance.
Okay, it is time to bring that big macro technology back down to the foundational circuit theory that runs the whole show. We have to talk about resonant frequency. And please, don't just view this as some boring textbook math. This is literally the ultimate make-or-break condition in electrical engineering. It is that one precise moment where the inductive reactance and the capacitive reactance in a circuit become exactly equal. For an engineer, this is a critical state. You either intentionally harness it to your advantage, or you desperately try to avoid it to save your multi-million-dollar equipment.
And this brilliantly illustrates the rule of opposites. In a series circuit, hitting that resonant frequency means your impedance drops to essentially zero. It acts just like a short circuit, causing massive voltage magnification. But on a parallel circuit, the exact opposite happens. Impedance absolutely spikes to infinity. It acts like a fully open circuit, which leads to massive current magnification. It is a night and day difference. And getting the two confused? Yeah, definitely not an option.
I absolutely love this piece of mentorship advice from Sir Abrar Ali. He urges us to learn these basic conditions before going out and looking for answers in complex textbooks. And it is just so true. If you don't intuitively grasp the difference between zero impedance in series and infinite impedance in parallel, reading some heavy manual on converter-based devices is just going to leave you totally frustrated. Your time spent mastering these basics is absolutely crucial.
Let's move on and see exactly how this builds in the real world. Section 5, real-world engineering stakes. So, let's take all this theory and apply it to a TCSC, a thyristor-controlled series capacitor. Physically, you've got a capacitor placed in series with your transmission line. But to actually manage and control it, you connect an inductor in parallel to that capacitor. Now, think back to what we literally just talked about. You are suddenly introducing parallel components into a massive, high-voltage transmission system. Based on our basic circuit theory, that introduces some very immediate, very real dangers.
Let's walk through this nightmare scenario step by step. Imagine your TSC is humming along, operating on the grid. Suddenly, the system's frequency, or maybe the specific firing angle being used, accidentally hits that resonant frequency condition we just discussed. Because that capacitor and inductor are connected in parallel, they instantly hit maximum infinite impedance. And boom, step 4. Your circuit effectively becomes fully open. The current has absolutely nowhere to go. This isn't just a chalkboard theory anymore. This is a full-blown catastrophic event on a live power grid.
And so the crucial takeaway here is the engineer's task. This is exactly why that foundational primer on basic circuit theory matters so much. Engineers managing these advanced systems have to actively and carefully manage those firing angles and system frequencies. They have to constantly monitor the grid to deliberately dodge this catastrophic open circuit trap. They are essentially playing a massive, high-stakes game of avoiding parallel resonance at all costs.
So I want to leave you with this thought to ponder. Knowing the destructive power of infinite impedance, how will you manage your system to actively avoid a catastrophic parallel resonant open circuit? Keep that specific question in mind as you continue your journey into power engineering. Because really, it's all about mastering the basics to safely control the future of our grids. Thanks so much for joining me in this analysis, and keep that curiosity alive.